Welcome to lesson 3-11A. Today we're going to talk about limiting reactants, and then I'm going to split this lesson in two by finishing with the other lesson in terms of theoretical yield versus percent yield. So let's look at limiting reactants. A stoichiometric mixture, it just looks at the relative amounts of reactants and products that you have. So for example, in this particular reaction, you have 3 hydrogen molecules, or 3 moles of hydrogen reacting with 1 mole of nitrogen. And so if you look over here in the before reaction, each subset here represents 3 hydrogens and 1 nitrogen. And so what that means is that for every little subset we have here, we get 2 molecules of ammonia. So we have 1, 2, 3, 4, 5 subsets. Over here, we end up with 5 subsets of ammonia. Now notice each particular subset represents this balance equation. That number 5 just happens to be what they drew in the beakers. But what happens if you have a limiting reactant? And so the reaction was 3 hydrogens plus a nitrogen gave you 2 ammonia molecules. Well, if you notice over here, there are 2 extra nitrogens hanging out. And so what's happening is the hydrogen is limiting how much you can form, because when you try to pair up and get these little subsets, there are some molecules left over, and those happen to be nitrogen molecules. And so after the reaction, you're going to end up with 3 little subsets of ammonia, but you're going to have those 2 nitrogen molecules still left over. So in this particular case, of your reactants, hydrogen is limiting because there aren't enough hydrogens to react with all of the nitrogens present. So a limiting reactant by definition is one that runs out first and thus limits the amount of product you can form. Some mixtures can actually be stoichiometric, which means they have just enough of all the reactants to form the products and there are no reactants left over. But then some mixtures, or most mixtures, require determining which reactant is limiting. And this particular concept is very important in industry because more often than not, one of the reactants is more expensive than the other. And so you do want to be able to look at a reactant and make sure you add enough of the other reagent to get it to all react. When we do limiting reactant problems, it's basically the same thing we've been doing with stoichiometry, only it's just added steps. We just have to do several more steps. To figure out what the limiting reactant is, we look at an equation, we use moles of different compounds because those are the relationships. We have to have the balanced equation to determine which one's the limiting reactant. And then most of the time what we end up doing is we end up computing the quantity of product formed. So the reactant that produces the smallest amount of product must run out first and be the limiting reactant. So we're going to look at a sample here. Nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. Other products of the reaction are solid copper and water vapor. If a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper 2 oxide, what's the limiting reactant? And it really wants to know how many grams of nitrogen will be formed. So the first thing we have to do is we have to figure out where we're going. We want to figure out which one's the limiting reactant because that information is necessary to determine how much nitrogen is produced. What do we know? We know the chemical reaction. We don't have it written or balanced yet, but we do know it because it was given in the prompt. There's the ammonia passed over copper 2 oxide, produces nitrogen gas, and it said the other 2 products were solid copper and water. And we know we have 18.1 grams of ammonia and 90.4 grams of copper 2 oxide. What information do we need? We need the balanced equation. We need to know how many moles of ammonia we have and how many moles of copper 2 oxide we have. So what do we use to get there? First, the balanced equation. So we have to step back and do an atom inventory and count and make sure we have the same numbers and types of each atom on each side. There's the balanced equation. My recommendation to you is go ahead and stop this video and write that equation and balance it yourself, but that would be the answer. What are the moles of ammonia and copper 2 oxide? So those are the molar masses. We looked at the periodic table. We figured that out. Now be mindful on this one. You had to know how to write that because copper 2 oxide, a lot of students will write it like this, and that is not correct at all. That 2 is simply the charge on the copper, and so that was a crisscross thing, and we reduced, and we just ended up with CuO as our formula. So be mindful of that. So all of this continues to build. Determined how many moles of ammonia. This is what we were given in the problem. There's our molar mass from up above, and we have 1.06 moles of ammonia. Same kind of idea for copper 2 oxide. This is what was given in our problem. This is from up here, and we have 1.14 moles of copper 2 oxide. So we have to determine the limiting reactant. What's the mole ratio? The mole ratio is 3 moles of copper 2 oxide to 2 moles of ammonia. So if we compare those, so if we have 1.06 moles of ammonia and try to figure out how much copper 2 oxide we need. So if we have this much ammonia, according to our balanced chemical equation, it's going to require that many moles of copper 2 oxide to react. When we just calculated on the previous slide, we only have this much. So this one is limiting our reaction. So before we have, so this is actually when we were given grams, we calculated our moles. And then when we went through, we're like, okay, if we use all 1.06 moles of ammonia, then that will require us to use 1.59 moles of copper 2 oxide, but we don't have 1.59 moles, so that's our limiting reactant. That's one way to do these problems. I prefer to do it this way because we're trying to figure out how much nitrogen we can produce, and so what we're going to do is we're going to start with each of our grams of our reactants and then go to see how much nitrogen is produced. So we have 1.06 moles of ammonia. What's its relationship to nitrogen according to the balanced chemical equation? So if we have 1.06 moles of ammonia, we should get 0.530 moles of nitrogen. If we have 1.14 moles of copper 2 oxide, balanced chemical equation, we should get 0.380 moles of nitrogen. Now, we can't get both of these because one of these is limiting. Well, which one produces less? The copper 2 oxide produces less. Therefore, that is our limiting reactant. So it's good to go ahead and figure out, like a lot of times they'll say how much product, how many grams of product. Go ahead and figure out those grams. Do the problem twice. Your lower number is going to be your limiting reactant. And if in that case, because that is the limiting reactant, we have to use that amount to calculate the N2. So when you figure out what the limiting reactant is, you can only use that amount to continue your calculations because using the other amount gives you false results. So there's our moles of N2, and ask for grams. So we use the molar mass. Notice this is N2 from the balanced equation, so it's 14.01 times 2. That's how many moles of nitrogen we got from our copper 2 oxide. And we go ahead and set that up to calculate how many grams of nitrogen we formed. So that's kind of a limiting reactant problem in a nutshell. I encourage you to pause that, process that, and so on, and work on several of those problems in the homework and any additional problems you can find, because it does take a lot of time, a lot of practice, and then next lesson we'll move on to theoretical yield and percent yield.